All right, so we've got the recording started. And the purpose of today's office hours are to go over any questions that you guys have on the week 5 conjecture. So I can share my screen and we'll get project guide for that. So on this conjecture, you start off with a couple specific patterns. And some of the patterns have like a multiplying effect, and some of them have an adding effect. So have you guys completed that part of the project, or do you guys need help with that part?
I need help with all parts of it.
Okay, we can do the whole thing. Okay, so if we start on this first one, what is the pattern that you guys notice in the values between each consecutive term? So you can either notice like a recursive pattern where it depends on the previous one, or you can also find the explicit one, which is what we're looking for, where you could just plug any number into it. Okay, awesome. So a couple people in the chat said that the pattern is that you're adding 6 every time. Yep, because like 8 plus 6 would give you 14, 14 plus 6 would give you 20, 20 plus 6 gives you 26, and so on. And then Melissa, you put in a explicit formula. Do you want to explain kind of your reasoning for that one? And how you know that that's...
Yeah. It's the second one. I mistyped on the first one, but I was just thinking since there's already 8 to start with, then we just add 6 plus whatever term we're on.
Okay, perfect. Yeah, and we could test and see if that's true, you know, by maybe like looking at the 4th term. So if we plugged a 4 into your equation for X, if you do 6 times 4, that would give you 24. And 24 plus 8 does equal 32. In a long day. It does equal 32. So that's true for like that specific term. And you could try it for, you know, any of the terms that were given. But it also makes sense because like to get to the 4th term, you had to add 6 like 4 times to get there. And what you were adding 6 to was the 8. So is everybody good with how Melissa's formula would tell us? And like if we replace the X with an N, that's what we could say the value of the nth term is. It doesn't really matter what variable you use, whether it's X or N. But does that kind of make sense to everybody why that formula would describe it? The nth term? Because it's like in order to get to the nth term, you would add 6, however many times n is. Does that make sense or no? I'm not really seeing any responses in the chat. Okay, awesome. Thanks, Anita. Samuel, we were just looking at this first pattern. And the way that Melissa described it, I'll put it in the chat again. It's 8 plus 6n. And her reasoning was because like if you start at 8 and then you add 6, like however many times to get to the nth term, like that describes the pattern that we're seeing in that table. Yeah, Amy, that would be more accurate. Yeah, it would be the value of the X term is that. Yep. Perfect. Okay, so that first one, it looks like we've got the expression for it. So now let's move on to the next one. So in this one, what do you guys notice about the pattern in the second table? Okay, doubling, multiplying by 2 twice the previous number. Yep, perfect. So all of those are describing a recursive pattern where it depends on the previous one to know what the next one is. Okay, and Melissa, you said that it's going to be exponential. Why is it going to be exponential?
Well, in my mind, at least how I understand it, is they're either adding the same thing every single time or you're multiplying it by the same thing. And so this is one of those multiplying where you're going to have to look at the previous term and then figure out what exponential thing you have to multiply by.
Mm-hmm. Yep, exactly. And like if like the connection between like repeated multiplying and exponents is that that's what exponents describe. You know, just like multiplication describes repeated addition. Okay, so like on the last one where we were repeatedly adding 6 n number of times, as a shorthand, we wrote that as 6 times n. And so in this case, if we're repeatedly multiplying by 2, n number of times to get to the nth term, how could we express that? And you're right that it will have an exponent in it. Mm-hmm. Yep, perfect, Amy. So if we write it down as 2 to the nth power, like let's say we were looking at the third term, that would mean we do 2 times itself 3 times. But 2 times itself 3 times actually equals 8 and not the 24 we're trying to get. So what else would we need to add to our expression to make it accurate? Mm-hmm. Yep, Tess, how did you know that it needed to start with a 3? Hmm. Yep. Amy, I think you mentioned that as well, that it's 3. And we would actually not do 3 plus 2 to the n, we would do 3 times it. Because we're doing like 3 times 2, however many times it takes to get to the nth term. Yeah, I assume that was probably what you meant, but yeah. And this is also helpful, like even if you were to plug in a 0, like if you put a 0 in the spot for n, do you guys know what an exponent of 0 equals? Mm-hmm. Yep, it always equals 1. And so even in that case, our formula still works because it's 3 times 1, which is just 3. Okay, so we've got our first 2. Does anyone have any questions on how we got those expressions? Then let's keep going. So I'll clear these drawings that we've got so far. Let's go down to these ones. So in this third table, the one with 5, -20, 80, and so on, what is the pattern that you guys notice on that one? Hmm? Yep, we're repeatedly multiplying by -4 to get the next term. So that's the recursive formula, which depends on the previous one. And maybe it's more accurate to put parentheses around the -4. But how would we write the equation for the nth term in that case? We got a couple different ones. So we've got 5 plus -4 times n. We've also got 5 times -4 to the nth power. So we can try these and plug them in. So like if we take a 0, and we plug that into both of these, if we do -4 times 0, that would be 0 plus 5. So this one works for the first term or the 0th term, I guess. And it looks like the second one also works for the 0th term because -4 to the 0 power, if we plug in a 0 to this end, that would be 1 times 5 gives us 5. So it's true in both cases. So maybe let's try the next one and see if that helps define it a little further. So if we plug in a 1 into the first one, -4 times 1 would give us -4. And if we add 5 to that, that would equal 1, but we want it to equal -20. So this formula won't work, but let's see if the other one does. If we do -4 to the first power, that's -4 times 5, that gives us -20. So it looks like that one would work. And if we tried it on the second one, -4 squared is 16. And does 16 times 5 equal 80? Okay, sweet. So this one works at least for the first 3 terms, so it's a pretty viable function. And if we think about like what it's telling us, like if we were trying to, or if we were gonna try to get to the nth term, it makes sense that that formula would work because we start with a 5 and then we multiply by -4, however many times it takes for us to get to n, which would be like multiplying by -4 to the nth power because you're repeatedly multiplying by -4, however many times it takes to get there. Is everybody good with that? Okay, awesome. So we're almost done with these example tables. Does anyone have ideas for what the formula for the last table might be? Okay, Jody, nice. So you notice the recursive pattern that you subtract 5 from the previous one to get the next term. Okay, Melissa said 9 minus 5x. Melissa, do you want to explain your reasoning for that one?
Yeah, so we the 0 term we start with 9, so we know that's going to be like the first thing we have to work with. And then we use the recursive formula and say, okay, what's happening every time? And we know we're subtracting 5.
Perfect. And why did you do 5 or like -5 times x?
Because the x is like our nth value, and so we know that we have to do, oh, it's not going to be negative, is it?
No, it is right.
Oh,
I was just wondering if you know why.
because you have, so it's 5 times whatever the value is, and then you're subtracting that. So if like on the second one, we know it's going to be 5 times 2, so 10. So it'd be 9 minus 10, that'd be -1.
Yeah, and technically you can think of that in 2 ways. Like you could think of it as 5 times n, and then you're subtracting it. Or you could also think about it as a -5 times n. Either way, like the notation is still the same, but the way you think about it can be different. And in either case, it does describe this pattern because you're decreasing 9 by 5 n number of times to get to the nth term. So it's kind of like on like that first one we were looking at where we had repeated addition. Like in this case, we have repeated subtraction, which you can think of as like multiplying by a negative number or subtracting the number times n. Either way, it's out to be the same. Is everybody good with that one? Okay. Awesome. So just so that it's all fresh in our minds, I want to go back and recap our formulas for all of these. So the first one, I believe we had 8 plus 6n, because you're starting at 8 and repeatedly adding 6, and you're doing that n number of times. So that repeated addition is where the 6 times n comes from. And then the second one, we have 3 times, what were we multiplying by here? I think it was 2, right? So we have 3 times 2 to the n for that one. And then we had 5 times -4 to the n for the next one. Because again, the repeated multiplication creates an exponent, because that's like how you denote repeated multiplication. And then for the last one, we had 9 minus 5n, I think. So those are the formulas that we found so far. So using these examples, we now get to create a conjecture that if the 0th term is b, where it can be any number, so like in our tables, we had a 0th term of 8, 3, 5, 9, etc. But if the 0th term is represented with a generic variable b, and each term is the previous term plus m, so m is the amount you're adding every time, then the nth term is going to be what? And then our second conjecture will be similar, except that we're doing the previous term times r. Okay, awesome. Yep, so we had several people in the chat who said that our conjecture for the first one, I'll fill this in, is going to be b plus m times n. And would one of you guys like to explain how you know that? That is correct. But how do you know that?
It's like the first one we did when we started with 8 and it was increasing by 6 every time.
Perfect. Yeah, so we've got this, like your starting term and then you're adding m, but you're doing it n number of times. So rather than writing it as like plus m, plus m, plus m, plus m, plus m, we just like notate it as m times n because that's the same thing as adding m a bunch of times. Okay, so that's great for our first conjecture. And then for the second conjecture, what would that one look like? So this time the 0th term is a, and each term is the previous term times r. What would the explicit formula look like in that case? Yep. Yep, you guys got it. So we would have a times r to the n. And technically, oh, sorry, I didn't mean to move that. Technically, you can write this just like that. Like you don't have to put parentheses in there. Sorry, I don't know how to make it line up with the lines again. But you don't have to put parentheses because of order of operations. Like order of operations says you always do exponents before you multiply. So that means that you do r to the n and then multiply by a, not like a times r and then multiply that number by itself n times. But I'm always fine if you guys put extra parentheses in. There's no problem with that if it's easier for you to think about it that way. Okay, so we've got our two conjectures. And before we go on to proving them, I want to point out like a connection to a algebra topic. I can't actually remember when it gets introduced. I know you like start introducing the concept of it pretty early in elementary school, but I don't know when the actual notation for it comes out. But you guys know the formula y equals mx plus b. I think that notation for it usually comes in like 8th grade or so. But conceptually, you guys introduce it a lot earlier. 7th. Well, Samuel, so you actually, like, if you guys have been reading the case studies, you know, like the penny tower ones, where they're like consistently adding like 3 coins every time. That's the concept behind it. Like, obviously you don't put it in this notation, but I think that stuff like that does get introduced in 3rd grade, doesn't it? Like in the context of like the penny towers or like patterns like that. Yeah. Yeah, so you definitely don't introduce notation, but I was like, I'm pretty sure that happens relatively early. Yeah. So if you guys look at this part of the formula, that's like basically what you guys found there. And so like usually this is introduced as like the equation of a line, but lines are just a way to like visually display patterns. And the basic idea of a line, you know, like this is the y-intercept, but the y-intercept happens where x is 0, or in other terms, like it's the 0th term. And then the M, or the slope of the line, represents how much you're increasing with each like increment of 1 along the x-axis. So that's kind of like a little connection to more advanced algebra. The next thing we need to do is we need to prove it. So we have our two conjectures, and our conjectures are clearly and concisely stated. If we wanted to use function notation to represent them, we could say that for this first one, that the nth term equals b plus m times n. Like if you want to write it as an equation, you could say that. And same thing for the second one, you could say the nth term in that case would be a times r to the n. So what we need to do now is we just need to prove that these two statements are true using the recursive formulas, or in other words, the pattern that depends on the previous term. So I'll go ahead and clear these really quick because I'll be able to remember those. So for conjecture A, and I kind of gave you guys like the structure of it. Basically, you would say that the nth term is that expression that we just found, the one that was, let me scroll up a little bit. So you'd say that the nth term is going to be b plus m n number of times. And if you want to, you can use function notation for that. And then it says the recursive formula for the value of the nth term is v of n, and if you want to, you can replace those with s if that's easier for you to think about it, equals the previous term plus m, because each term in the sequence was defined to be the previous term plus m. And then for the base case, we just need to prove that it's true for the first term. So according to like the problem that was given to us, the 0th term is b. So we just need to prove that f of 0, because that was our first term, really does simplify to equal b. So does anyone have any ideas of how we could prove that? Usually with the base case, you like just plug the number in. So what would we get if we plug in a 0 into our conjecture expression? Perfect. Yep. And then how can we justify that that equals b? Because ultimately we need to show that it really does equal the original expression we were given. Yep, exactly, Tess. Yep. So when you do m times 0, anything times 0 equals 0 because of the identity, no, not identity, 0 property of multiplication. And so by the 0 property of multiplication, that part's going to equal 0. And so that means that your 0th term is just b. So the base case should usually be really easy to prove because you just plug it in and show that it equals it. And then for the induction step, we're going to assume that the conjecture is true for the n minus 1th term. So if we assume that this statement is true for n minus 1, what would that expression look like? Is like that's how induction works, is like you assume that it is true for the previous term, and then you use that assumption to prove that it's true for the like current term you're working on. So like notice where the n is here, and notice that we're plugging in an n minus 1. So what would that look like? Yep, exactly, Melissa. Yep, so this is going to be our assumption. we're going to assume that it's true for the n minus 1th term. So we're assuming this. And then what we want to prove is that the nth term equals this. So using our recursive formula, we can rewrite that, or we can write the nth term, because we know that the nth term equals the term right before it plus m. So we can take this expression and plug it in up here, which would give us our nth term equals b plus m times n minus 1 plus m. And how can we get this to look like this?
Well, don't we need to distribute the M into
Mhm.
the what's C's?
Yep, we could do that. So if we distribute the m, that would give us mn minus m
Plus M.
plus m. Mhm.
And then the M's cancel out because
Yep.
minus M plus M.
Perfect. And we did it. Because that's what we wanted to prove.
Just
Yeah,
one
and it,
question.
oh yeah, go
Um,
ahead.
So when you go, you have that line draw to the blue part up there. What's like
Mhm.
the math language to say that I'm going to this point?
Let's see. So the way I would describe this is I would say, okay. Sometimes it's kind of hard to do it on the spot. So I would say, because each term is the previous term plus m, because that was like part of the information I was given in the problem. I would say because each term is the previous term plus m, the recursive formula for the nth term is this. And that is something that was also given right here. And because I assume that my conjecture statement, so this statement, because I assume that that's true for the n minus 1th term, I can substitute b plus m times n minus 1 for the n minus 1th term. So substitute, I think, would be the word you're looking for, because you were asking, like, how do you describe that fact that you plug it in?
Yeah.
Yeah, you'd say that I substitute the expression b plus m times n minus 1 in for the n minus 1th term.
Okay, so I just want to make sure I'm understanding this. So you're using the one that's circled to the left in red, and you're plugging in what we just did for n minus 1.
Yeah, so the one that I circled in red, that's our conjecture statement that we're trying to prove.
Uh-huh.
And the way that you do a proof by induction is you first of all prove that it's true for the first term, which in this case was the 0th term. So you prove that it's true for the very first one. And then the idea of induction is you assume that, like, whatever term you're looking at, so the nth term, you assume that the term right before it follows the rule that you're trying to prove. So since we're trying to prove that the term is b plus m times n, if we assume that's true for the term right before the nth term, that means that it's going to be b plus m times n minus 1, because n minus 1 is the term that's right before the nth term. So that's an assumption that you make, and then you use that assumption to prove that it's true for the nth one. And the reasoning behind, like, why that logically proves that it's true for every number is because if you prove it's true for the 0th term, then, and you also prove that for any term, the one right before it implies that it's true for the term that you're looking at. That means that the 0th term implies that the first term is true, which implies that the second one is true, which implies the third and the fourth, literally on for infinity. So it's, last office hour, I described it as like kind of like a domino effect. Where like proving that the 0th term is true and proving that any previous term implies the next one is true. Basically like topples all the dominoes out to infinity. I don't know if that answered your question.
I think so. I guess I was confused about the plus m. Like I love your explanation. I just was one more question to follow up. So the plus m you have up there, so it says f of n minus 1 plus m.
Yeah,
I get
this one
confused
right
with,
here.
yeah, right there, yeah. That
Mhm.
plus m, that's where I get confused with where does that necessarily come from? Because when I look at the f of n formula, I see the m times the n. So is that
Mhm.
n represented by the f of n minus 1?
Yeah, so this formula right here is coming from the recursive formula.
Oh, okay, thanks.
So the recursive formula is the one that depends on the previous one. So
Right.
recursive formulas are not very useful like by themselves, because in order to find like the 100th term, you have to know the 99th term. But they're very helpful in induction because the whole point of induction is to assume your conjecture is true for the n minus term or n minus 1 term, and then use that to imply it for the nth term.
Okay, I think I figured out. I didn't realize that the base case and the induction steps had two separate formulas. Because you use the recursive one for one, then you use like the f of n formula for the other.
Yes, so both of them will use this formula because
Uh-huh.
that's the one we're trying to prove. But in order to do the induction step, you do need the recursive one.
Right. And I just didn't connect that there's the two different things. So thanks.
Yeah, thanks for clarifying. Amy, you said you had a question about the first and 0th term?
Yeah, when you just did that one, okay, so going back where you have conjecture A, it says if the 0th term is B,
Mhm.
and then each term after that, or sorry, each term is a previous term plus M. Okay, so based on that, but then you come down to the base case, my conjecture is true for the first term because F to the 0, so it's showing that F to the 0 or function when 0 is the input
Mhm.
is b plus m times 0. So you want to, when you do the base case in this, since 0 is part of our series, is that why you want to use this? Because I know in our previous one, we used f of 1 because 1 was our first thing in the series. Is that how you do this?
Yeah, and technically you could do either one. Like if you wanted to think of the first term as being F1, it
Because
would
that's
still
what
be
I
true.
did.
Yeah, you could totally do that because that would be B plus M times 1. You would just need to explain why that is the first term by the definition of the way they gave you the pattern. But that's not that hard to do because you say, well, the 0th term was B. If you add M to it, that term is going to be whatever B plus M is. And our formula also gives us B plus M. I just think
Because
it's a
that's
little
what I
easier
had
to
done.
use 0.
Okay,
Yeah,
so
and
you can do
you can do
either
it
way.
either way.
Okay.
Yeah, because the base case is kind of like your first domino. It's like tipping the first domino. So you can start at the 0th domino and tip that one, or you could tip the first one and it would still have the same effect of knocking over all the rest of them. Do that. All right, awesome. Any other questions or clarifications about this one? Okay, sweet. Then let's go ahead and move on to the next one. So I'll clear that. And for this conjecture, the conjecture we came up with earlier was that the 0, what was it? I think A times R to the N, I think was how we defined it. So this is the one we're trying to prove. Okay, so for that, we need to prove that the conjecture is true for the first term, and I'm going to think of this as like I'm going to identify the first one as being like the 0th term, because I like plugging in 0. So if we plug in a 0 into the statement we're trying to prove, what does that give us? And actually, probably it might be more like easy to understand it if we rewrote that as the 0th term, just so we're not like confusing, like, is it the first term in the sequence, or is it the term that's labeled as the first term? Like term number one. So, sorry if that is a distracting tangent, but if we take a 0, plug it into the statement we're trying to prove. Okay, perfect. So we have a times r to the 0. And according to the pattern that was given us, the 0 term should be a. So how can we justify that this equals a? Hmm? Yep, perfect. Yep, that's one of the exponent properties. I don't actually know what the name of it is, but basically the exponent rule that says any number to the 0 power always equals 1. So you could use that to justify that this equals a. And that would prove our base case. And then what are we going to assume for our induction step? Remember, all induction steps start with the same assumption. You're assuming that your conjecture is true for the term before the nth term. Okay, so Amy, you said f of n minus 1 equals, I'm guessing the 6 was meant to be a exponent sign. And it looks like Anita got a times r raised to the n minus 1 like that. Perfect. Okay. Okay, awesome. So we're going to assume that. And ultimately, what we want to prove is that this is true for n. So we're assuming the term right before n follows the rule. But we want to prove that the nth term also follows the rule using that assumption. So what would be our next step to prove that? So like, since we know that, or we're assuming that this equals this. Yep, Amy, and we specifically, like, justify that by saying that the recursive formula for the nth term is f of n equals n minus 1th term, times r. And then, like you said, we would take this and plug that in. So that's gonna give us f of n equals a times r to the n minus 1 times r. And then how could we get this to look like the conjecture we're trying to prove? Okay, yep. You could say r equals r to the first power. So we could rewrite it like that. And then how do we get that to look like r to the n? Yep. Yep. Yeah, so what Amy put in the chat, so Amy said f of n equals a times r to the n minus 1 plus 1. The justification for that is the product rule of exponents that you guys proved in, I think it was week 3. or no, maybe week 2. But the way that it looked when you guys proved it was, like you had different variables. It was like x to the a times x to the b. And you guys said that this equals x to the a plus b. You guys remember that? I'm pretty sure it was week 2. So that's kind of the reasoning that we're using here, because these are the x's, and then you're taking the exponents and adding them. And then like Jody said, our next step, or our last step really, would be just to simplify -1 plus 1 equals 0. And so you'd get f of n equals a times r to the n. Yep. And then you'd be done. Any questions on any of that? Yeah, Melissa, so the conclusions for induction, it's like usually always the same, you know, like, because I assume, like, because the n-1th term implies it's true for the nth term, like, that domino argument can be the same for all of them. Like, so the conclusion you guys wrote last week, you can copy and paste it and just substitute in the, like, other, like this specific situation, but the conclusion for induction is almost always the same. So like, when mathematicians who do lots of proofs, like often, usually their conclusion will just be, therefore, by the principle of induction, the statement is true. But since you guys haven't really done a ton of induction, I want you to make sure you understand how to explain it. But if you already explained it in last week's, conjectures, then you can just kind of copy and paste and change whatever details need to be changed for the specific conjecture. Yeah. The main thing in a proof by induction is the induction step, because usually the base case is really easy. And then the conclusion is the same every time. You know, it's like, oh, the 0th term implies the first term, and the first term implies the second, and the second implies the third, and so on and so forth forever. But the induction step is where the bulk of the work comes in. Any other questions? All right. I will stop the recording then. And if any of you guys have any other questions about anything else, feel free to stick around. Otherwise, I will see you guys next week.